Alright, what's up, guys? Let me get situated for a moment. Alright, here's our first problem, fluid mechanics. So we're gonna just dive right into it. Approximate the pipe size required for a pipeline carrying 250,000 standard meter cube per hour of natural gas, which is kind of like CH4 at 20 atm absolute. That's gonna be important. And 20 degrees Celsius. So the equations we're going to use to solve this problem comes from McGraw-Hill's Chemical Engineering Series, Unit Operations, 7th edition, Chapter 8, the equations on Chapter 8. All right. Um, this is a very good book. It got many chemical engineering concepts. I got the book with me right now. Let me see. Yeah, I'm talking about it got fluids, heat transfer, uh, mass transfer, distillation, distillation columns, and all that type of stuff. Membrane separate. This is a very good uh, resource for chemical engineers. So I advise y'all to get. Well, this book is expensive. I think when I was in college, it cost like $400 or something. You know what I'm saying? And Lord knows how much it costs now with this inflation. So it may be pushing 800. Who knows? But yeah, this is just a pipe sizing problem, approximation. Um, so so just pause the video and try to work it out by yourself, and we will go through the solutions and see what you come up with. All right, just pause the video. All right, guys, this is the solution I came up with. I worked this problem by myself, of course. Just let me know if you came up with something else or if I made a mistake or anything. Just let me know. I'm not always right, you know what I'm saying? But let's get into it. I want y'all to understand where I got all this stuff from, uh, stuff like that. All right. So basically, we gotta. Let me see if I can. There's something I can do here. Green. What's this? No, let me see. What is that? Highlights and notes. Oh, well, I can't do none of that. Still trying to underline. Okay, I'm about to get into it. I just want to play around with it. This is I'm still trying to learn this stuff. Okay. All right. So we got preliminary pipe size. We're trying to size of a pipe, transcontinental pipe that's carrying 250,000 standard meter cube of natural gas, in which we will say that it's CH4 mostly. So at a pressure of 20 atm absolute and 20 degrees Celsius. So we can just convert that to degrees Fahrenheit. See, the thing that y'all need to know is how to convert SI units to English units. Learn how to be, you just need to learn how to oscillate between the two. Because in your courses, they're going to, well, my course when I was when I was in Mississippi State, we did number English units, and when I was in junior college, it was nothing but SI units. So uh, it was a big thing. I was just making mistakes and everything. So y'all need to learn both SI units and English units. Okay, there's some other units, but we never touched those. So you got to know those too. But I really doubted that it would be used in practice, but we'll see. All right. So first off, we know at standard conditions it's basically 1 atm, uh, 1 atm and 25 degrees Celsius. And in English units, uh, it's 32 degrees Fahrenheit and 29.92 inches of mercury. But those want to know what's 29.92 inches of mercury. So it's 29 point. I did the calculation, down here, 29.92 inches of mercury times 25.4 millimeters in every inch times 1 atm in every 760 millimeters of Hg. Cross out your units equals 1 atm. So that's what it is, 1 atm. Or you can say 14.7 psi. I just want to show that to y'all. Now, and also I just want to say units. You want to, units gonna eat your lunch. All right. If you want to be a successful chemical engineering student in your courses, always look at the units, follow the units. Um, every time you do your calculations, write out the units, cross out and everything. Because when I was in school, I'd be missing, like getting wrong answers because I didn't pay attention to the units. It took me a while to realize how to cross out units and stuff like that. So I don't want y'all to be making that mistake at all. Um, I'm talking about units, and in y'all courses, units will eat y'all lunch. But on this channel here, we over here we ain't worried about units because y'all gonna master the units and everything. So if units come to you trying to eat your lunch, saying, "Do you want to eat your cornbread?" You say no. Go on, get your own cornbread. Okay, I'm just playing. All right. Um. So then we gotta convert the 32 degrees Fahrenheit into Rankine. Um, you already know, just add 460 to that, and that'll give you 492 degrees Rankine. Now, hold on, let me explain this at the top. I forgot to explain this at the top. So this right here, your molar volume, is at um, your molar volume. Um, that is actually given out of the book on chapter 8. I forgot to reference that. But anyway, we you know that at 32 degrees Fahrenheit and P equals 29.92 inches of mercury, you get a molar volume of 359 feet cubed per pound mole. Now, how did they establish that? Well, basically, ideal gas law. That's in chemical engineering. In your courses, ideal gas law will come up like numerous of times. So you got plenty of time to learn that. But that is, if I would say what comes up mostly in your chemical engineering courses, I'll say ideal gas law. So it's good to know that. And so now we need to find the molar volume at a state of a temperature that's what was it? Yeah, at 68 degrees Fahrenheit in 20 atm. Absolute. So ideal gas law, PV equals nRT. Now here, y'all know what's going on right here. We took the PV equals nRT at one state, then divided by PV equals nRT at another state, at point 1 and at point 2. So basically, when you do all that and you do some algebra or whatever, carry to the top or whatever, you know how you do. You get V2 dot, which is the flow rate, divided by V1 dot, which is, the flow rate, equals T2 over T1 times P1 over T2 times R over R, which is 1. You can cross those out. And N2 dot over N1 dot. Now, why is that crossed out? Is on the principle of the conservation of mass. Basically, N equals out. But that's going to be in another video that we'll do in mass and energy. When I start doing mass and energy type problems. Right now I'm just doing fluids. So here we go. 528 divided by 492 times 1 atm divided by 20 atm. Units give you a unitless number of 0.05365. Now with that you can find V2 by multiplying by 250,000 meter cube per hour times, in every foot. The way I got this, in every foot, if you look at your table of conversions, in every foot there is 0.3048 meters, and so you have to cube it. Wherever you do, you have to cube that term to get feet cubed. So you got to cube 0.3048 meters, cube that, make it meter cube, times 0.05365. That's your ratio to convert it into V2, and that would give you. I rounded that number up, so if y'all get something close to that, that's good. I rounded it up like a bunch, so it should be roughly 474,000 feet cubed per hour. And they talk about sig figs, but I never really learned it because they never tested you on it really. So for all those people that say sig figs, sig figs, well, we ain't gonna worry about sig figs here. So, okay. Now here another concept will pop up in your classes. Uh, Find the density of a gas. One of the most simple ways is use ideal gas law. Um, Rho, which is density of your gas, is equal to P molecular weight divided by RT.
You still up there?
No,
Oh, okay. Make sure you turn the lights
no.
on. All right, good night.
Good night. Alright, sorry for the real cut. Okay, sorry for the real cut. Got disturbed. Okay, P equals okay, rho, the density of your gas equals the pressure times the molecular weight divided by RT. So the molecular weight of CH4 is 16. That's some little chemistry for you. So you got 4 hydrogens. That's molecular weight of 1 plus 12 plus 12, which is your carbon carbon atom will get you 16. So 20 times 16 times 14.7 psi per ATM times 144 units. Your R value that you need to use here is 1,545.3 and times 528. That's 528. I made a mistake though. So I give you a density of 0.830, 0.830 pound mass per feet cube, which is roughly what that seems to be right because the density is pretty low. The density shouldn't be like 62 or high. You know what I'm saying? With that, you can use that to find the mass flow rate by multiply the density times the volumetric flow rate, in which what we found right here. Multiply those two together, and I wanted a dynamic unit of seconds. So we know 1 hour is 3,600 seconds, and that comes out to be 109 pounds per second. Now, this right here is a relationship that you need to know involving the mass flow rate, density, area of the pipe. A is the area of the pipe, and U is the velocity. But we run into a problem. What is the velocity? We know the density, we know the mass flow rate, but we don't know the area of the pipe. That's what we're trying to find. And also, we don't know the velocity. Now, right down here, this comes out of the chapter 8 of the book that I referenced earlier in the video. That yeah. So this is an empirical equation. So um, meaning these gotta be in a certain units. The density gotta be in certain units. The mass flow rate gotta be in certain units. Then it spits out an answer in a certain units. Even though if you actually try to cancel your units out, it won't look right now. But anyway, the density is supposed to be in the book. Density is supposed to be in pound mass per feet cubed, and the mass flow rate has to be in pound mass per second, which we already calculate that. So we plug into 12 times 109 divided raised to the 0.1 divided by 0.830 raised to the 0.36 give you 20.5 feet per second. Now, in literature, when I say literature, I mean out of the book. Well, never mind. 20.5 feet per second. Now we can calculate the area of the pipe using this equation that I put here. So you do 109 pound mass per second divided by 0.830 pound mass per feet cube times 20.5 feet per second. Units. That give you 6.41 feet squared. Let's give you, if you convert that into inches squared, it'll be 923 inches squared. Now let's find the diameter of the pipe. We can find the diameter of the pipe by square root of 4a divided by pi. I'm just assuming y'all know all this, but if you don't, look it up. So doing that, plug and chug, we come out to be a 34.2 inch diameter pipe. This is, a little bit under 3 feet diameter pipe, transferring that natural gas, CH4, that is. So yeah, if you got any questions or if you got a different answer, please let me know in the comments. I might link my email if you have a better, a different solution, because I can be wrong. You know what I'm saying? So just learning as I go. And I'm glad y'all here to, trying to give y'all value to help you study for your courses, your classes. Typically, this may not be the type of problem you see that I think you'll see, because this equation right here, we didn't go over this equation right here. So, but all the other stuff, you might see it in your courses, especially the ideal gas law. You'll see it. Whatever. So, all right. That's it. Please like the video if you want to see more content. Holler back at you.